For over a century, we've had this one fundamental rule drilled into our heads. Nothing, and I mean nothing, can go faster than light. It is the absolute bedrock of modern physics. But what if I told you that a forgotten thought experiment from Albert Einstein himself, the man who literally built his career on that speed limit, actually revealed a crack in that very foundation? And what if I told you that when we finally tested it, reality turned out to be far, far spookier than even he could have imagined? Okay, let's get into it. So, is there anything faster than light? The short answer is, surprisingly, yes. But it's the long answer that's truly going to bend your mind. It forces us to rethink the very nature of cause and effect, and it might just be the best evidence we have that we're living in a multiverse. All right, to get why this is such a revolution, we have to talk about a core idea in physics called locality. The concept is actually pretty simple. For something to affect something else, a signal, something, has to travel between them. There's no such thing as instant action at a distance. And this is where you can really see the huge problem Einstein solved. In Newton's world, if the sun just vanished, the Earth would instantly fly off its orbit. But Einstein saw that this would create insane paradoxes. Someone flying past Earth could actually see the effect, the Earth careening off into space, before they saw the cause, the sun disappearing. So he fixed it. In his theory, gravity is a ripple in spacetime, and that ripple travels at the speed of light. That way, everyone, everywhere, agrees on the order of events. Cause always comes before effect. So here's the bottom line. Locality is what protects the timeline of our universe. It's the law that says you can't have an effect without a cause that got there first, and the absolute fastest that cause can travel is the speed of light. Every classical theory we have obeyed this rule, and then quantum mechanics came along and crashed the party. And this is where the story gets really, really good. Because Einstein, the guy who established the cosmic speed limit, was the very first person to find a theory that seemed to break it. He saw something deep inside quantum mechanics that he called an entirely peculiar mechanism of action at a distance. And listen, this wasn't some one-off argument. This was an intellectual war that raged for decades. It kicked off with a simple but profound question at the legendary Solvay conference, got sharpened into this brilliant paradox in 1935, and finally, almost 30 years after that, became a real, testable experiment. Okay, so let's unpack Einstein's first attack from 1927. He told his colleagues, look, imagine an electron. Quantum mechanics says its location is just a wave of probability, spreading out across space. But the second you detect that electron at one spot, poof, that wave has to instantly vanish from every other possible place in the entire universe. Instantly, to make sure you don't find it somewhere else. Think about that. Instantly, across any distance. And this quote just nails his objection. I mean, how could a measurement right here instantly affect the state of things way, way over there? To him, this seemed to be a flagrant violation of locality, which meant it was a violation of his own theory of relativity. Now, this sparked a huge philosophical fight. Einstein was convinced that quantum mechanics had to be incomplete, just a shadow of a deeper, more sensible local theory. But Niels Bohr, who was the champion of this new physics, basically argued that asking what an electron is really doing when we aren't looking is a meaningless question. All that matters is that the math correctly predicts what we measure. But Einstein was not done, not by a long shot. In 1935, he and his colleagues Podolsky and Rosen dropped the famous EPR paper. And in it, they cooked up a thought experiment so clever, so powerful, that it pushed this whole debate to the absolute breaking point. Okay, so imagine you create two particles that are linked or entangled. Their total spin is zero, which means if one is spinning up, the other has to be spinning down. But here's the quantum catch. Neither particle actually has a definite spin until you measure it. So let's say you separate them by light years. The moment you measure one and find it spin up, the other one, no matter how far away it is, instantly becomes spin down. This was Einstein's checkmate move. He had completely cornered quantum mechanics. This bizarre outcome had to be explained in one of two ways, and to him, one of them was just completely ridiculous. So here was the choice. Either reality is fundamentally non-local, and there really is a spooky action at a distance, or there's no spookiness at all. Einstein proposed a much more sensible idea. The particles had their instructions from the get-go. They were like two sealed envelopes, one with a card that says up, the other down, decided the moment they were made. This explanation, called local hidden variables, saved locality. It saved common sense. For decades, that's where things stood. It was just a philosophical debate, because both explanations gave the exact same results in every experiment. It seemed impossible to ever know who was right. Then, in the 1960s, a physicist named John Bell came onto the scene. He'd always been bugged by the weirdness of it all, and he decided to take another look at Einstein's old argument. And what he came up with was pure genius. Bell figured out that if you added a little twist to the EPR experiment, basically by giving the people measuring the particles a choice of 3 different angles to measure from, the two theories could no longer hide behind each other. They would be forced to predict different results. And this slide right here is the climax of the whole story. Bell's math proved it. If quantum mechanics and its spooky non-locality were right, the measurements would disagree 25% of the time. But if Einstein's sensible, predetermined reality was right, they had to disagree at least 33.3% of the time. The very nature of reality came down to a number. So all that was left to do was run the experiment. Decades of debate between the greatest scientific minds in history, Einstein versus Bohr, it all came down to this one test. The equipment was built, the particles were entangled, the measurements were taken. 25%. Over and over again, in labs all over the world, the answer that came back was always 25%. Einstein's common sense local reality was wrong. The universe was spooky after all. The result was absolutely staggering. It meant that Einstein's suspicion was right, just not in the way he'd hoped. Quantum theory is non-local. Our universe is connected in a way that just defies our everyday intuition and seems to defy the cosmic speed limit itself. And don't just take my word for it. John Bell himself couldn't have put it any more plainly. His work proved that any theory that wants to correctly describe our universe must include influences that travel faster than the speed of light. There's just no local way to explain quantum entanglement. Okay, so this is probably the question screaming in your head right now. If influences can go faster than light, does that mean we can send messages into the past? Does this break causality and allow for time travel? And the answer, incredibly, is no. It turns out the universe has a very clever loophole. While the influence is instant, the outcome of any one measurement is completely, totally random. You can't force a particle to be spin up or spin down. So even though their fates are linked, you can't use that link to send a message. Locality is broken, but somehow causality is miraculously saved. But there is one final, truly mind-bending way out of this whole mess. What if the problem isn't the signal, but the idea of collapse itself? The many worlds interpretation says that when you make a measurement, the universe doesn't pick one outcome. Instead, it splits. A version of you sees spin up in this universe, while another version of you sees spin down in a new parallel universe. If that's true, no faster-than-light signal is needed because both things happen. Locality is saved, but at the cost of an infinite number of parallel worlds. And so, in the end, Bell's theorem pushes us into a corner with two equally astonishing choices. We have to either accept that our universe is fundamentally non-local, with real influences that break the light speed barrier, or we have to accept that we live in a constantly branching multiverse of parallel worlds. Which reality is spookier? Well, that's a question physics has left for us to ponder.